All right, so welcome back to the final part of this model checking tutorial. I realize it's quite late in the day, and it's the fourth talk today, and I also realized I've been introducing lots of new notions. I mean, lots of decompositions and width, and here an edge, and there an edge, and there's a cover and another cover. So it would be perfectly natural if you were a little bit confused about all these things. But today, in the last one, I want to speak about sort of something a little bit different in the sense of what we've seen so far with the underlying major techniques we use in this area and sort of closed projects, in a sense, because the sparse case is completely solved. We know how it works. There isn't so much you can do about it. And the next part and the last part is current research, if you want. I mean, we want to go beyond nowhere dense and beyond sparse classes. And this is called stability in graphs for a reason you'll see in a moment. Okay, so the main question I want to speak about in the next hour and a half, there will be a break in the middle and so on, so take it a bit slowly. So what happens if our classes are not sparse? Yeah? And in particular, it means what happens if you can't close them naturally undertaking subgraphs? Yeah? Because we know what happens when you close them under subgraphs. The answer is there. So now we look at classes of graphs which are not closed in the subgraphs. They're defined by some structural property, but if you take the subgraph closure, this property will no longer be true. Yeah? And the simplest example would be the class of complete graphs. Yeah? It's clearly very dense. I mean, you have every edge there could be. It's very easy to model check anything on complete graphs because, I mean, a complete graph is the same as having no edges at all. But as soon as you start closing them on the subgraphs, you get every graph at all. I mean, existing. So you can't just do it. No? And so we need something else to help us. Yeah? Well, because I haven't been speaking about lower bounds, you haven't seen the main argument why we need all the subgraph closure all the time. Yeah? But yeah, well, something like this is just required. Right, so what can we do? This is a tiny, you've seen this picture before, and it's the same thing. You can't read it, but you've seen it. This is the answer for sparse classes, so where do we go from here? Yeah? And we want to prove more results, publish more papers, yeah, so something needs to be done. One thing you can do is, well, we do what we always do. Yeah, that will be the first part. The second one is, once we've done it, we can interpret what we've done. And the last thing is we make it stable, and this will be the most interesting part at the moment. So what do I mean by all of this? So the first thing, the first option you have is you do the same thing that we've been doing on sparse classes. So we start initially bounded degree classes. We got a model checking attractability result. We had trees, and it was extended to treewidth, and we had this result. And all of this, everything I presented in the last 3 times 1.5 hours, it was basically driven by the idea I take a class that exists in the literature, which has been studied. We have all the structural techniques and decompositions and theory behind it. And I try to show model checking results on it. And then as soon as you've done it, you go to the next higher level. Yeah? And now in the dense world, we could do the same thing. Yeah? We just look at natural classes of dense graphs, which have been studied, and which we understand somehow. You can read this up on them in the literature, and then we try to prove results. Yeah? And this is a good starting point because you need to develop new techniques in the same thing. You know, this whole idea of decomposing something into smaller graphs and making it empty in a constant number of rounds, it's not going to work in the dense world, right? Because it's dense. Huh? And so we can just try this, and it has been done. And I do not want to speak much about this here, but just to give you a few examples. So one class of dense graphs which has been studied are interval graphs. Yeah? It just means you take a set of intervals of the real line, yeah? And every interval becomes a vertex in your graph, and there's an edge between 2 intervals if they overlap. Yeah? This is called an interval graph, and of course you can generate any size of cliques, yeah, if you want to just take overlapping intervals all the time. Yeah? And so basically, Gagnon, Lenny, Karl, Jarlek, Schwartz, and Teska, they prove that if you, for some subclass of interval graphs, you get tracked to a first-order model checking. There's a little bit of technical, there's a technical side condition you need in the proof, which is this. So if you have a finite subset of reals and a first-order sentence, and then you can decide in n log m time with an n input graph defined by these intervals sort of gives you, satisfies the formula. Yeah? And I do not want to make precise what this is actually. Yeah? So it's just one class of graphs you can study. Okay, let's, another example is this one, which is maybe even more natural. You take partially ordered sets. I mean, an order, just a linear order is the natural example of an extremely dense graph, yeah? Because if you take it as a graph, it just there's a vertex between an edge between any pair of vertices because they are related by the order relation. So that will generate just cliques. But you can also study partially ordered sets, yeah? And it's not possible to get really tractability results there. But you need to restrict this class of partial orders, and the width is just the maximum size of a sort of anti-chain, and the height is sort of the height of the order. And so there's an algorithm. If you have a partially ordered sets of width W, and they can be colored by a certain number of colors, and you have a first order sentence, then you can decide whether it's true in this partial order. And the time you take, it's dependent on the width of the element times its quadratic number of vertices in your partial order. I mean, vertices, I say vertices because I'm always thinking about graphs, but of course it's an element in the order. Yeah? And partial orders are, of course, another very natural example. And you could actually start doing other structures. I mean, why not look at groups, or why not look at anything else that there is? I mean, there's life beyond graphs, even if it's hard to imagine. But you could do this, yeah, and people are studying this, I suppose.
Why does the sentence need to be negation normal form? I don't get it.
I don't know.
If it's not, just push negation and make it negation normal form.
No, I don't know. I mean, I just copied it from the paper, actually. I think it's, well, because initially they had this for existential formulas. Yeah? Existential formulas, and so you need negation at the inside, obviously. And then it was improved, but never mind exactly. It's not my theorem, so I'm just copying it. Well, there's some reason. Okay, no, let's not go into it. There's some reason for it in the paper, but it doesn't. Okay, there's a notion called rank width. It's a generalization of treewidth. Yeah? And so if M is O1, if you don't have quantification over sets of edges, you can solve this on every class of graphs upon a clique or rank width. It's the same concept. Yeah? And my feeling would be you can't go beyond. And ideally, because we proved this lower bound for MSO2 and treewidth, ideally it would prove the same thing for rank width. But the structure theory is not good enough at the moment because you don't know what happens if the rank width is very high. There's something in your graph, but you don't know what it is. I mean, the problem here is if you do this, there's no real candidate for an optimal class because in the sparse setting, it became clear sort of along the way that, I mean, nova dense would be what we aim for. Yeah? It was a matter of proving it, and but it was always clear, I mean, along the way, sort of, this is what we should be doing, in a sense. Yeah? It only took us 6 years to prove it, but I mean, it was always clear this is what we wanted to do. Yeah? But here it's not so clear. I mean, what is the largest, at the moment we don't have any largest sort of natural candidate for a dense class we could take. Yeah? Well, beginning, whatever the beginning is, yeah, but I mean, my beginning is this. Yeah? And no, well, yeah, it became along the way, very early on, it became sort of the natural target in a sense. And like I said, I mean, there's this theorem that you can't go beyond nova dense. It was 2009 or so that we saw this. Yeah? So it's 6 years before, 5 years before we proved the bound. Yeah? And at this point, of course, it became clear you can't. This would be a natural limit. Yeah? And here I don't know of any such class. I'll present something later on what could be a candidate, but it's very far from any good estimate. So this is not something, it's very worth doing, but I'm not doing it, so I'm not speaking about it. The next option is something a lot more interesting, which is a very promising idea, which is interpretations, first order interpretations. And so let's speak about this. So let's say we have a class of graphs for which the model checking problem is tractable. Yeah? Could be nova dense, for instance. Yeah? And now you define for every graph in your class, you define the complement graph. It has the same vertex set, but you flip edges and non-edges. Yeah? So the edge relation just becomes the opposite. Yeah? And then you get a new class of graphs, C bar, which just contains the complements of your graphs in C. Yeah? If C is a sparse graph, a class like binary degree, then the complement will be extremely dense. Because let's say if you start with a degree 5 class, then every vertex in the complement has all the neighbors except for 5 at the most. Yeah? But you haven't changed much for model checking, yeah, because it's very easy to see that the model checking problem for this class is still fixed point attractable. Yeah? So do you see how it works?
Just flip all the answers, the leaves.
Yeah, you can't flip the answers, yeah, but yes, exactly. Yeah. Because if you give me a graph in this class C bar in the first order formula, all I'm doing is I replace in this formula every atom saying there's an edge between x and y by its complement saying there's no edge between x and y. I get a new formula phi prime, and if you look at this, well, phi prime will be true in the graph G if and only phi is true in the complement graph. If there's an edge here to satisfy this atom, then this edge is lost here, and so the non-edge will satisfy this formula. And so just complementing a graph takes you into a very dense class, but it doesn't change anything for model checking. Yeah? And so we could just use our model checking algorithm for C to solve model checking on C bar. Yeah? And this is a trivial example, of course, but it shows us the final answer can't be sparse. I mean, it has to be something more interesting. And you can now ask, well, can I do something more general than this? I mean, if you subdivide every edge once, for instance, again, this will not change first order tractability, but it could completely change the class of graphs. And so the answer is yes, and there's a very well-established notion in logic which is exactly doing what we need. It's called an interpretation. And here I do a simple version of it. It's called a simple first order interpretation in graphs. Yeah? And this just consists of a formula theta with two parameters x and y. Yeah? And so just take any first order formula with two free variables, x and y. And if you give me a graph G, and actually I have this pointer, then this formula defines a new graph on top of this. Yeah? It's theta of G. We have the same vertex set, but now the edge relation of the new graph is just a set of all pairs of distinct vertices u and v which satisfy the formula. I mean, you just take your graph, I mean, you go through every pair of vertices and check whether it satisfies the formula. If it does, then you draw an edge between them, and if it doesn't, you don't draw the edge. Yeah? And so this formula in any graph defines a new graph, yeah, which you just get by evaluating this formula in the graph. Yeah? And here this would be one example. If theta is just a formula saying not exy, then the graph you generate is just a complement graph. And so this is the simplest and most trivial form of what's called a logical interpretation. In a more general statement, you can have more relations and higher arity relations. Yeah? So if you're really working on structures and of higher arity, then you just take formulas that have more free variables, and they define a new relation in the same way. Yeah? But if you like databases, and at least one in the audience probably does it, it's like this formula is just defining you a view on your database. I mean, I think it's called a view. And you could just take this as new relation in a new database, and this is defined. But of course, you can also think of more general interpretations. For instance, you could change the universe of your graph. Right? So you can have a new formula saying, in the same way as you start defining edges by a formula, you can also define vertices by a formula. So you could add a vertex formula saying phi of u, and you only keep the vertices which satisfy the formula. And you can take this even more general. You can have a formula, something like, yeah, with two free variables, and you could just say this is also defining the universe. Yeah? So the universe of your new graph just has all pairs of vertices satisfying this formula. Yeah? That would be a new node. And then you have a new formula defining edges among these pairs, and you can think of many, many ways of this. And so there's a very general and well-established, and most logic books will have a good chapter on it.
Let's look at this. Still, you start from a single structure and you create a new structure.
Yes.
What about other things? For example, what happens if you take a product of two graphs? What happens to the product of two dense graphs? So that will give you another way to kind of reduce, to give you basically a way to reduce the problem. I don't have the intuition if the product of two dense graphs is dense or not. This can take take you out of the picture.
You end up in hell if you do this. The product of two dense graphs, you end up in, it kills everything.
Well, but you should still be able to do this kind of the same reduction to the underlying model checking problem. So that's another way to, it's not exactly an interpretation, but it's another way I think to give you
I think the problem is that if you have the product of the two graphs, then you do not see actually the structure of the product in the graph. So
no. I mean, it depends on what you define by a product. But here's an example for a product.
The domain is the pairs of edges, and there is an edge if the two edges exist. This is standard notion of product.
You could just take this formula to define the universe. True, yeah. And of course, the edge relation could be defined by I draw an edge between x, y, and x prime, y prime, if x equals x prime, and there is an edge between y and y prime.
Standard notion of product requires edges between both, right? It's standard notion of product. You said there is an edge if you have both. But the point is you can combine two graphs now. It's not just the power of the graph. You can take two graphs.
Yeah. Well, this isn't, yeah, well, if you have two different graphs, this takes you somewhat out of
it's not a first order interpretation, but I think it still has the same feature that you are able to reduce the model checking problem for the product graph to the underlying model checking problem for each of the underlying graphs.
Yeah, you could just say if you have an evidence class of graphs and you take the disjoint union of two members, this will still be no evidence, and then you color one copy of your graph green and the other red, and then there would be a first order interpretation generating the product of this again. Yeah? And yeah, so you could do this. Right? The interpretations are really a very general way of generating one graph from another. And so the obvious question could just be, no, I wish I hadn't scribbled all over the place. Okay, this is the main notion, the main concept we need about an interpretation lemma, which is if you have a first order formula in a graph, and if in this formula replace every occurrence in the simplest form, let's say, of the edge atomic formula saying there's an edge between x and y by this new defining formula theta in the simple case, what you get is a new formula theta of phi, which is true in the original graph if and only if phi is true in the created graph. So the picture you can draw is you have this theta, and it takes a graph to a new graph theta of g, which you construct from it by evaluating just the formula. And it takes a formula back to the formula that speaks about the old graph. Yeah? And satisfaction is preserved. Yeah? So this is if and only if. Yeah? And in the simple case, it's not very hard to see because, I mean, what does it mean in the new graph to have an edge? Yeah? It's just, there's an edge in the new graph if the end points of this edge satisfy the formula theta in the old graph. Yeah? And so all you're doing, this formula transformation is sort of reversing the construction of your graph. So it's not very surprising, and it's very, very simple to prove that this is true. But this works for any type of interpretation, even extremely general ones, where you have sort of complicated formulas defining your universe, and you have equivalence relations on them, and so on. Yeah? So what we get from this is it's a first order definable way of taking one class of graphs which we understand, and from this generate a new class of graphs which we would like to understand. And it comes equipped with a sort of reverse engineering of formulas from the new class of graphs to the old class of graphs. Yeah? And if you look at this, it's very nice, right? Because what I want to do is I want to look at no-evidence classes of graphs, and I want to study what can you obtain from them by first-order interpretations, and I want to generalize the model checking results. Yeah? And it looks like this is exactly what we need, because you take your no-evidence class of graphs, you generate a new class. I want to verify whether the formula is true in a member of this new class. And this gives me the way back to say, okay, I can actually verify this by checking a different formula in the old graph. The main problem is, I mean, it's not all algorithmic. I mean, this is easily done, yeah, but this also. But you're not given G as input, yeah, because you're given this graph as an input and this formula as an input, and the question is phi true in this new graph? And you need to find a way to actually construct something in your old class which would generate it. And if you could do this, then this interpretation lemma would just say, okay, if there's a polynomial time procedure that takes you from this graph to this graph, then you can just easily extend model checking results. Yeah? And for instance, here in this case, there is, of course, a polynomial time procedure. You just flip the edges. Yeah? In general, this might be very complicated, yeah? And it's not clear what happens. Yeah? And so the model checking idea I just described, I have a class of graphs which has tractable model checking. I look at the class of graphs that's generated by this first order interpretation, and I would hope that the model checking problem for this is FPT.
You know, there is the result from MSO about essentially, I think it's the same kind of FPT or linear time FPT with the Courcelle hierarchy. And there we start with trees, then you close them under MSO interpretations and under unwinding. And you get, again, a hierarchy, and you get the same, essentially, I think it's basically, you get the same kind of that MSO is you get FPT with essentially linear time over a very large class by iterating these two operations, MSO interpretation and unwinding.
Well, I mean, the Courcelle hierarchy is not so much about model checking. It's about, I mean, first of all, it's infinite graphs. It's about decidability. I mean, what it says is, if you have a class of graphs for which the satisfaction problem for MSO is decidable, then you can take these operations and it will still be decidable. Yeah? So decidability just means you take a class of graphs like the class of infinite trees, and the question is, if you give me an MSO formula, can I decide whether it has a model in this class?
It's also about model checking.
Yes, but only for theoreticians. Infinite graphs.
Yeah, that's why model checking is a non-trivial problem.
Yeah, but you have the point is you have a finite representation of the graph. So it is a model checking problem because you're given a finite. All of them are finitely representable.
Yes.
So you're given the representation and you're asking, that is the formula true? So it is a more general model checking problem where you're dealing with the representation rather than an implicit representation, rather than explicit representation, the way we assume here.
Yes, but
once you go to this to representation, the difference between model checking and satisfiability become fuzzy.
Yes, yeah. But the problem doesn't disappear, right? Because also in the Courcelle, if I give you a graph of level 19 of this hierarchy, if you want a model checking, you need to trace it back into the, you need to unwind all these operations that got you from a tree to this point. Yeah? And so there needs to be a computable and effective way of doing this. Yeah? And for decidability, it's not so important, because you know there is some tree that does it. Yeah? But for model checking, you need to do this somehow. Yeah? And if you can find a way of doing that, then you're happy, yeah? But this is a good result. I mean, I guess most of you will not know the Courcelle hierarchy, and I will not explain what it is, but it's just, it's basically an extension of this idea, because interpretation is just one operation that takes you from one class of structures to another class of structures, yeah? But in theory, of course, and in practice, I mean, in research practice, you could ask for different operations. I mean, you could study just, I mean, it would be very interesting to study operations that take you from one class of graphs to another, preserving model checking results. Yeah? And this Courcelle hierarchy is one set of operations that you start from trees, and then there's a constant number of operations you can do that take you sort of upwards this hierarchy. And it preserves decidability, and I didn't know about model checking, but if there's an effective way of getting back this hierarchy, then it preserves model checking. Yeah? But it's exactly the same idea, yeah? And then, of course, and this is a very good way of studying something, yeah, because it's interesting in a sense, yeah, and it takes you from something you know to something else, because you're not actually having to redo all the algorithmic stuff. Yeah? And clearly, if you want, let's say, if I was dreaming and I had a precise characterization, a property P of classes of graphs, which precisely characterizes tractability for first-order logic, then it would have to be closed under all these operations. I mean, every set of operations taking you from one class to another, preserving tractability, it would have to be closed under it. Yeah? And so it's worth actually exploring ways of transforming graphs without destroying tractability of model checking. Yeah? And the most obvious starting point, I mean, Courcelle is sort of the same thing, except then you unravel, is this one. Yeah?
In addition to imputation, we mentioned before another operation, right, which is taking the joint union of two graphs with colors to distinguish between them, and then do on top, right? So you can create levels here, kind of the same way.
Yeah. There's a whole set of operations you can take, in essence, yeah? And you should take. But because it's a finite amount of time, yeah? And let's stick with simple interpretations for the moment, yeah? for the rest of this next couple of minutes. Yeah, and so the general model checking idea is you have a class of graphs for which you know how to solve to evaluate formulas efficiently, and then you apply this interpretation to get a new class. And then ideally, the model checking procedure you could do is you get some graph as input from your new class and a formula, and you want to know whether it's true in this graph. Then you first reverse engineer your formula. You compute this one. That's trivial because if you know the interpretation, then this comes for free. Right? So, and then you want to verify whether, well, if this formula is true here, if and only if this formula is true in the original graph that this one came from. Yeah? And this you know how to do. Yeah? And so the only remaining step is how actually can you go from here to here. And for this, we can actually assume we know the interpretation because it's, there aren't too many interpretations you can use. But it's still a computational problem how you go back. And so here's one very nice result. Well, we've actually been talking about this for many, many years. We should do it. And then some people actually did this, which is better than talking about it. And the first case they studied with bounded degree graphs. So you take a class of maximum degree D and close it under some simple first order interpretation, and what do you get? You can get something, yeah, but it can't be very complicated. If you think about it, it cannot be very complicated, because if you think of Guyfon's form in vertices like a couple of neighbors, and they have a couple of neighbors, but basically if you have a first order interpretation, then whether there's an edge between two vertices, it will only depend on their neighborhoods unless they're very close together. Yeah? And then, so it will be very, very uniform graph. Yeah? And I think I could make this a little bit more precise, saying if you think about this, if you take two vertices and you look at their three neighborhoods, yeah, let's say the Guyfon form is radius 3, and you take two vertices which have the same three neighborhoods and they're far apart, they will have exactly the same neighbors except for those which are very close, yeah? Which is so close that the first order formula can mention them explicitly. Yeah? And this is the idea behind this definition, what they have. So let's say we have a general graph G and we have a number k, and we define a relation on this graph called the near k twin relation. Yeah? And so it's defined by two vertices u and v are near k twins, yeah, so they're in row k because it's easier to speak. If the symmetric difference between their neighborhoods has at most k elements. Yeah? So you take the set of neighbors of one vertex and the set of neighbors of the other vertex, and then you compare them, yeah? And so it means they have almost all their neighbors in common except for at most k. Yeah? K is a constant. And this is a relation you can do. It's not an equivalence relation, certainly, so it's not so useful. But you can just say a graph G is K0P near uniform if you can find some number K for which this near K twin relation is actually equivalence relation on your graph. Yeah? And it's not hard to see that this near K twin relation is not an equivalence relation in general, yeah? Because if A and B have almost all neighbors in common except for K, and B and C have all in common except for K, it doesn't mean that A and B have the same neighbors. Yeah? And so clearly not every graph will be K0P uniform. And this P just means you look at the index of your equivalence relation, and this is number P. And you can extend this to classes of graphs. So a class of graphs is K0P near uniform if every member of this class is K0P near uniform. And it's near uniform if there's some integer K0 and P for which it's uniform. And this defines you any class of graphs. Just some random definition you can take, and there will be some classes that you will have it, and others will not. And so it's just some definition. Yeah?
Sorry, dumb question.
Yeah.
Does index P mean equivalence classes have size P, or there are P equivalence classes?
P equivalence classes.
And the theorem then that they proves, which I think is a very, very nice theorem, is, okay, there's a nice theorem, it's not a very, very nice theorem, but the next theorem they used to prove it is actually a nice one. They show that you can do efficient model checking on this class C. Yeah? So if you have a class of graphs which is K0P near uniform, then the first model checking problem is fixed point injectable. Yeah? Yeah, the obvious question is to ask, well, why should we care? I mean, you can, of course, you can make some technical definition and then prove a result, but why would you care? Huh? And the only reason to do this, if this class is actually somewhat interesting, it's natural in the sense of you know how these graphs look like. Yeah? The beautiful theorem they prove is that these classes you get by this are exactly those classes which you can get by first order interpretations from classes of graphs of bounded degree. Yeah? And this is very nice because it just means we have a natural class of bounded degree graphs which we understand and which somehow appears and we like it. We know how to do model checking, and if you close it under first order interpretations, then you get exactly this. And I think this gives a lot of justification to studying these kind of things.
The theorem you should drop the K0p, right?
Yeah. And of course the theorem is stating it the wrong way around, because this is not how you do it. I mean, you not define something and then look for another class of graphs which you can that gets you this by interpretation. But the real way of doing it, we want to study class of graphs we know and close them on interpretation and see what happens. And this is the answer for bounded degree. The real question is actually, can we characterize class interpreted in other sparse classes? Start with trees. What is the first order closure of trees? And what about class of graphs interpreted in over dense classes of graphs? And that would be the ultimate thing we could hope for. I mean, nice to understand this. And this is a very interesting approach, I think. And we are actively doing this at the moment for bounded expounding classes. And I'm not sure if everybody in the audience agrees, but there's some conjecture what we would get. And I was actually hoping that we would prove it by today, but we haven't yet, so I'm not speaking about it. But maybe next time. But I think this is a good way to go, because we get natural new classes, we understand them, we get model checking, and it's conceivable to think that if there is a natural limit like nowhere dense in the sparse world, then there would be the interpretation closure of these classes would sort of have something interesting to say in the dense world as well, because there seems to be something natural going on. But this is as far as I know. We don't know how it looks like. I mean, no evidence closure of interpretation. So let's go to the next option, and this is what I want to speak about in the rest of this talk, making it stable.
But you didn't answer the question if you go back one slide, which is suppose that we have such a class of near uniform class. So one, we have to, of course, find the parameters. But do the result also tell us how to go from such a graph to the underlying?
This one doesn't, but this one does. I mean, this is one lemma you need to show where you come from.
The theorem shows you how to go back, how to invert. The theorem
just gives you an algorithm that constructs from a K0p graph the old one. Yes. But I mean, to do this, you need to know these bounds, and that's why they're in the theorems. Because somehow, I mean, how do you define such a class of graphs? I mean, you need some implicit definition, and the implicit definition here are the bounds K0 and P. But if you know K0 and P, then you can construct this. And this, it's not very hard. I mean, I don't want to dismiss the result. I mean, no, you know this. It's not very hard because it's like many proofs, of course. Because bounded degree, I mean, there's sort of there isn't much you can say about bounded degree graphs in first order logic. Like I said, I mean, it's bounded degree. If you have a constant radius, there's only a constant number of neighborhood types you can have. And your formula will basically just say you connect every pair of vertices of a certain type combination or you don't. And the only exception you get if something is very close to each other. And this is how you get up with this. But still, of course, you need the algorithm coming back. All right, so I promised Mikolai I would do a 10 minutes break, and maybe this is a good point to break because we're speaking about something completely different. So I would like to speak something completely different. Well, not completely different, but quite different, which is the last option. The first option was basically look at classes we know and like, and then try to find results. The second option was closer to the third I want to speak about now. We start from sort of sparse classes we understand, and then close them under some transformation of graphs. And here the example was first order interpretations because they're well established, but as Moshe pointed out, you can take any kind of transformation and hope that would preserve attractability. And the third option would be we could start looking at parameters of dense graphs, which if you apply them to classes of graphs closed under subgraphs, that would give you something like nowhere dense. I'm not sure if this was very clear, but we have this notion of nowhere dense, and in the sparse world, I mean, okay, you take class of graphs closed under subgraphs, and we know nowhere dense is the final answer to model checking. Now let's say we study classes of graphs which are closed under induced subgraphs. It's the slightly more general step from arbitrary subgraph closure. And it's realistic to hope that we can get a characterization of these classes of graphs, which are closed and induced subgraphs. Yeah? And what would be a very natural candidate for sort of the most general type of these classes you could hope for? Well, we don't know what the answer is, but one way to look at it would just say we look at classes of graphs which are closed and induced subgraphs, defined by some structural property, and ideally, if we apply this property to subgraph closed class, it should be nova dense. Yeah? Because then there would be some, I mean, if on subgraph closed class it would be less than nova dense, then it's probably not the most general type. And if it's more than nova dense, then it cannot have tractable model checking. Yeah? So, yeah, you could just look around for all sorts of graph parameters and just try to find some that's equivalent to nova dense if you're in the sparse world. And it turns out there's such a thing. Yeah, so so can we find a characterization that has a meaningful definition in dense graphs, but also meaningful definition, of course, in the sparse world, which is the same as nova dense. Yeah? And because it's reasonable to assume that, I mean, maybe there's nothing so really special about nova dense. Maybe there's a way more general sort of parameter or sort of structural property which explains tractability, and it just happens to be, if you close it on the subgraphs, it just happens to be nova dense. Yeah? And it's quite likely, I mean, could be true, could be not true, yeah? But well, why not? Yeah? It's just maybe we are putting too much emphasis on sparse graphs. Yeah? These are the prime objects and well-behaved and nice, but maybe there's something equally nice and which is far more general. Yeah? And yeah, so this is what we can look at. And so thankfully there are such things. Yeah? And so there's a theorem, yeah. If you want to know these kind of things, then graph theory is not the answer anymore. You go to model theory and they study these kind of things all the time. And so there's a theorem by Adler and Adler. This is not a typo, there are two Adlers. So what they proved is the following conditions are actually equivalent. There is a concept of stability in model theory. It was developed by Shrilar, and it's a very well-established theory that, there's, I mean, like these model theories do. I mean, there are tons of concepts and classes and properties and so on. One is stability, one is dependency, or the dependency is actually the not independent property. And what they proved is that if you have a class of graphs closed in a subgraph, then this class is nova dense if and only if it's stable, if and only if it has the non-independent property. In fact, it does not have the independent property. This is what NRP stands for. And of course, you don't know what stability and NRP, or you may not know what it means. But these might be candidates. Yeah, we could just ask, okay, well, let's look at stable graphs in more generality, because they would actually correspond to the nova denseness in the sparse setting. Yeah? And so they might be a good target. Huh? And the NIP, yeah, okay, NIP is NIP is NIP, and you need to really understand what it's saying, and it's not so easy to define what it's saying. So let's refocus on stability. Yeah? And so what does it mean to be stable? So we have a class of graphs, and we look at a first order formula, just any formula, and there's two sequences of free variables, x bar and y bar, and they have always the same length. Yeah? And it has the order property within the class C of graphs. If for every length n, yeah, you can find a graph in your class, and you can find tuples a1 to an and b1 to bn. This I should, this should be 1. Yeah? So you have a1 to an and b1 to bn, so that this formula is true for a pair AI and BJ, yeah, this should be J. I'm sorry, this is full of typos. Huh? If and only if I is less than J. Yeah?
Okay, now I'm sorry, but now you're confused. Okay.
Yeah, I know you're confused, but don't read it. See,
X bar and Y bar are vectors of variables.
So much for the not reading. I'll show you the example first, and then you ask. Yeah? This is what it defines. Yeah? The picture is true. The definition sort of has the typos. Yeah? So this should be J, and this should be I, and you have two tuples. Yeah? So what this formula defines is the following. It's called a ladder. Yeah? So you have a sequence of vertices here. Let's just assume B bar is just a single element. Yeah? And you have a sequence of vertices here, n of them. And then B1 has an edge. I mean, an edge just means it's an edge defined by this first order formula. So we saw before the break that we have, if you take a first order formula with two free variables, it defines a near edge relation. Yeah? In the same way, of course, you can take a first order formula that has two sets of free variables x bar and y bar, and then you can just take every tuple for interpretation of x bar as an element and every one for y bar, and then it defines an edge relation on these tuples. And this is what you see in this picture. Yeah?
No, but the thing, I have a problem with the types here. X bar is a tuple of variables, right?
Yeah.
N variables.
K.
K variables.
Yeah.
Where does K come from?
Yeah, well,
K variables.
it's always K.
So what,
any logic
but
is
AI bar is an individual element in your
No,
notation.
it's a vector.
No, this is a vector, but it has some finite length, and the length of this is the same as this.
So the A1 to AN are N K tuples.
Yeah, the n k tuples. This is why the bar is on top. Yeah, this is a A1 bar and a n bar. And this n here is this n, and the length of this vector is just some number k, which is fixed. Yeah.
Two N tuples, I mean K N tuples, N K tuples, sorry. N K tuples A1 to AN, and another N K tuples B1 to BN.
And you could take it as defining a bipartite graph where one partition are the tuples A1 to AN, and the other one is B1 to BN. Yeah? And so this is the bipartite graph. And you draw an edge from BI to B to AJ if they satisfy the formula. Yeah? And so what it's supposed to define is this thing which we call a ladder. So B1 has an edge to every A. B2 has an edge to every A except for the first one. B3 has an edge to every A except for the first two ones. Yeah? Which means B1 and AI will always satisfy the formula. Yeah? And B2 and AI will always satisfy the formula unless it's A1. Yeah? And B3 will satisfy the formula with every A except for A1 and A2. Yeah? And so on and so forth. And the last one only defines this. Yeah? And the class C of graphs is stable if there's no such formula within C.
So this is parameterized by n, I guess?
Yeah.
So it's n stable or something.
No, it's not
For
unstable. It's stable.
For every N.
It's stable if you're not unstable, let's say. Yeah. Which means if you're not stable, then it means you have a first order formula, which for every n you can find a graph, and in this graph it defines a ladder of five.
Yes. Okay.
So there's a first order that defines your arbitrarily high ladders in your class. So why is it called order property? Because if you take the obvious perfect matching on this, connecting every pair of AI and BI, and you contract these edges of the matching, you get an ordering, basically.
So in German you said it's not stable if Ordnung muss sein.
Yeah, sort of, yes. No, actually, this is okay. Let's not. No, go on. Like I said, I'm trying to squeeze something out of you, which is on camera. But anyway, yeah, but we don't want any order. Yeah, that's the point. Yeah, because we want this to be messy and untidy. Yeah, because the class is stable if you can't define. I mean, this is the other way of thinking about it. The class is stable if you can't define arbitrarily long orders in your graph. Yeah. And this is a concept that comes from model theory, and ordering is somewhat bad in a sense. So things are not ordered, and because in ordering every two elements are comparable somehow. Yeah? So you can say things about these elements. If you look at the Geifman graph, I mean, Geifman theorem, it was saying a first order property is just something you can define locally by looking at R neighborhoods. But if you have an ordering, then the R neighborhood is just the entire order because everything is comparable. Yeah? And so Geifman theorem doesn't say anything if you have a linear order because everything is so close. Yeah? And it's always nicer to have many elements which are not connected in any form. Yeah? In the extreme case we've seen in the previous part, which is bounded degree graphs, almost any two vertices have nothing in common. Yeah? They're very far, and in an order this is harder because everything is close. Yeah? And so a class is stable if you can't define these ladders, which means you can't define high orderings. And I'll try to make any sense of this in the next couple of slides. So here are examples because no valence classes. They are stable for this reason I just stated, because let's say if you had a no valence class which was not stable, it means there's a definable formula that it will contain this ladder basically. Yeah? But this would be a very dense subgraph in a way, right, that you would have.
But there's this first order formula used to define this. So.
Yeah. No, it's not so trivial, and therefore I will not do it. And we just say, for the rest of this talk, just assume a class is stable if you don't have any lattice as induced subgraphs. Yeah, this is the definition I will now work from on. So because just for those who repeat it, because you know this for the rest of these next 10 slides or so. Let's just assume a class is stable. I define it now like this. It's stable if you don't have any induced subgraph, which is such a ladder of any of long height. Yeah? And then it's obvious that no-dense classes will be stable in this sense, because if you had such a thing of this is dense graph, yeah? Because you can contract this as a one contraction, and no-dense class are closed on the contracting edges. Yeah, and so you would get a large clique as a depth 1 minor, and you shouldn't get. Yeah? And therefore, you can't have this in.
No, but this is an interpretation. Really, it's not that the graph doesn't have this order.
This is what I was saying. I'm repeating it here. I'm changing it for the rest of this talk to make it easier. The definition, and I just define a class to be stable if you don't have this as an induced subgraph. Yeah. So the formula would just be EXY. Yeah? Okay. This is actually a good way of saying this. Let's assume the formula that's defining your order, it's stable if the formula EXY doesn't define you such a thing. Other examples are those which are cliques. Yeah, because in the clique, I mean, there's nothing definable in a sense, and you will not get this, yeah, because everybody is connected to everyone else. So it's in the clique you can't. Okay, this vertex you have, but you won't find someone like this, because it's not. You can't just delete this edge. If you had a real proper first order formula, you could delete any constant number of edges. But I mean, if you need a really high ladder, so it will never be like this. And of course, it's easy to see in the clique you can't define a linear order on these vertices. It's just a random set. Yeah? Non-examples, and this is bad news, are classes of graphs of bounded clique width. And I haven't defined them, and I will not define them. But this is a class of graphs where we have first order model checking which is structurable, and so this already destroys hope that stability will be the answer. And these things are closed on induced subgraphs, so stability is not. On the other hand, it's way more general than clique width. All right, and so let's start looking at stable graphs. Yeah, and I haven't much to say about this in terms of model checking because I don't know what to do with it. Yeah, but it's still worth looking at because something very nice comes out of it, and I think it's a very nice class of graphs to study, nevertheless. Yeah? And so the first paper I know that was really studying this explicitly in terms of graph algorithms is this one by Maliares and Schiller. So let's see, be a stable class of graphs, and you take a graph from it. Then you can find for every epsilon, you can find a number m, which has this property. Okay? So if you take a large enough subset A, so the graph is very big, and you take a big number of vertices in it, then you can partition this thing into S partitions. Yeah? And this is at most m pieces. So you split it disjointly into at most m pieces. And basically, the connection between two different subsets is uniform in a sense. Either you have all edges between two pairs of vertices, or you have none of them. Yeah? So this would be a perfect world. You could just say, I want to be able to sort of split my graph into some number of subgraphs. And if you look at any pair of them, then either every vertex here has everyone here as a neighbor, or every vertex here has none of them as a neighbor. It's a very, very regularity condition you have. Yeah? And so your graph would look like this more or less. Yeah? But within two classes of, let's call these things classes here. But basically what you're saying is two different vertices here will relate to one here in exactly the same way. Yeah? This would be perfect. It's not exactly true, but it's almost true. Yeah? This is called, there's a general theorem, it's called regularity theorem, and this is just an extension to stable graphs. Yeah? And so the precise conditions maybe are not so important, but it just means if you take every vertex here has all of these vertices here as neighbor except for a very small fraction, and the fraction is 1 over epsilon. This is the epsilon you see here. And in between them, it's either an independent set or it's a complete graph, except for epsilon exceptions. But I'm not using this, so don't read this too precisely. I just wanted to state the real theorem because it's actually true. What I'm saying is not, but I mean the intuition is this. Yeah? So you can partition it to some number of constant number of subsets, and in between them they're extremely regular because nearly every guy behaves in the same way with respect to the outside. It would be very, very nice if it was really the same way, but there's some distortion, and this is just this epsilon, which means except for a very, very small fraction of these, any two vertices here are the same. You've seen this near twin relation where we said two vertices are near twins if they have almost the same neighborhood except for a constant number of exceptions. Yeah? And that's the same here, except the exception is a fraction of the size of your graph. And this is very useful for all sorts of algorithms. Because approximation, for instance, yeah, you can use it. It's very nicely. I just want to put it out because it's a starting point of what we're doing in this paper. And there's one technical tool I want to present. And I know it's late, and I know it's the last talk, but on the other hand, it's the last talk, so you can also safely forget about it because I will not be speaking any further about it. But it's an extremely nice thing called indiscernibles. And it's a technical tool in these results, which you get, and you get very efficient results from this. And so let's define it. We have a graph, yeah, and we have a set of formulas. And we call the sequence of elements A1 to AL from our graph, they're indiscernible with respect to this set of formulas. If whenever you take a formula from your set, yeah, it has k free variables, and you take two subsequences, yeah, or I1 to IK, or J1 to JK of this long sequence, then one satisfies the formula if and only if the other one satisfies the formula. Yeah? And the only requirement you need is they have to be in the same order. So let's draw a picture. Yeah? You have this set of vertices, and red is actually an awful color. Okay, you have this A1, A2, A3, A4, and so on. Yeah? Okay. This is very long. It's a long number of AL, actually. Yeah? Yeah. And now you have this formula. It has k free variables. Yeah? Obviously, k needs to be smaller than L, otherwise you can't do anything about it. And what it says is just, it doesn't matter how you pick your elements from your set, yeah, from your sequence. One choice of elements will satisfy the formula if and only if the other one will. So you could just start in saying, okay, well, I want this guy and this guy and this one and this one. Yeah? And your neighbor could just say, no, I want this one here and I want this vertex. And yeah. And then the condition is actually the first sequence will satisfy the formula if and only if the second sequence. Yeah? And the only requirement is you can't change the order of elements. Yeah? And such a sequence is called indiscernible if it's indiscernible in this sense for every formula in your set delta. And you see there's an obvious reason why it's called indiscernible. Just assume that your set delta is closed in the permutations of the variables. So if you have a formula in it with x1 to xk and you permute them, it will also be in it. Then it just means any set of vertices you pick, yeah, any two sets of vertices you pick will behave exactly the same with any set of formulas. Yeah? So they're indistinguishable by these set of formulas in your set. Yeah? And this looks like a useful property. Yeah? I mean, if you have a huge number of vertices which you can't distinguish in any form, then this is nice, yeah? Because they behave the same in the same. And so the theorem you could prove is if you have a stable class of graphs and a finite set of formulas, then there's a polynomial, and this is surprising that it works. There's just a polynomial p of x, and for every member of your class and every number m, and any sequence of vertices of length p of m, so a1 to a p of m, any vertices you want, you can find a subsequence of it of length n, which is indiscernible with respect to your set delta.
So this is like a polynomial Ramsey kind of thing?
I wish you hadn't asked. Yeah, but it's a polynomial. Let's keep it this way, because it's nice that it's polynomial. I mean, Ramsey usually takes you, let's say it this way, it's not very surprising that this works. Yeah? Because you start with a very, very long sequence, and then you apply Ramsey arguments to find sort of subsequences that satisfy. I mean, for every formula you take on k variables, Ramsey will tell you have a subsequence of size that's indiscernible with this formula. Yeah? But Ramsey has a big, exactly, and well, Ramsey is not he wasn't a small man, he's a very tall guy. And you can do it in polynomial, and this is a surprising part. Okay, maybe just repeat the argument. How would you construct this sequence? Let's say you have a formula of k variables, and you want to find an indiscernible subsequence of this huge number of vertices you have. Yeah? So you can color by Ramsey. Do you know Ramsey's theorem? Who doesn't know Ramsey's theorem? It's hard to do. Okay, yeah, no, you see it. The Ramsey's theorem just says if you have a, okay, you take a long list of elements, yeah, and you color any constant size subsequence of it by some finite, okay, you have a finite set of colors, yeah, and any subsequences of k elements you assign a color to it. Yeah. And then Ramsey just says if your sequence is long enough, then you will find a subsequence in which any subset of size k will have the same color. So the simplest version is for graphs. I mean, every graph has a huge independent set or a huge clique, which is just if you have only two colors. Yeah? But this is a more general statement, but the bounds are not very small. I mean, they're exponential and they're no good bounds. Yeah? And so if you give me a very long sequence of elements and the first of the formula of k free variables, I just label every k element subsequence by 1 if it satisfies the formula and by 0 if it doesn't. Yeah? And then I apply Ramsey to it and I would get a subsequence where every k elements, either all of them satisfy the formula or not. Yeah? And then you do this for every formula in your set, but, and then you would get an instant sequence. But this is very efficient, yeah, because it's a polynomial. And this is, turns out to be an extremely useful tool, actually.
Can you say anything about the degree, or it just depends on delta and C in some theories?
Let's keep it like this.
Yeah.
Well, otherwise we spoil the fun, yeah, but let's keep it like this. And this sequence can also be computed very efficiently. If you follow the proof, then it can be computed in polynomial time. Yeah? And the degree of this polynomial depends on delta. So this is nice, yeah, because it's nice. And why is this nice? I mean, why would you care at all? Because what you can basically do is whatever you want in your graph, yeah, you can try to formulate it in first-order logic, and then you get something which is indistinguishable. I mean, you get a huge set of vertices, and they are indistinguishable with your property. They will all have the property. And here's an example for it, and I uniformly quasi-whiteness. It's a property from finite model theory, actually, which is equivalent to being nowhere dense if you have subgraph closure. And it's a very useful property I want to explain. Okay, so a class of graphs is uniformly quasi-wide if the following thing happens. And the best way of understanding what it says is to draw a picture, because then it's not very hard to see. And what does it mean to be uniformly quasi-wide? It says the following thing. You take a graph, yeah, and I would like to find a scattered set in it, which means a set of vertices of pairwise distance 2 times r, let's say. Yeah? And you can see a reason why I would like to find this, because Greifen's theorem requires me to find these elements. So I want to find this set B, which is 2r independent in G minus S. But if you're nowhere dense, then you may not have such a sequence. There could be a vertex that's neighbor to everyone else. Yeah? So there isn't such an independent sequence. Yeah, but this is what I want to find. So a bunch of guys which are far apart. And it turns out I can do so, and I can do it even better. Because if you tell me a subgraph, I mean, you just give me a set of vertices yeah, and ask me to find a 2r independent set within this set. Yeah? So I want to find it not just anywhere else, I just want to find it in here. Yeah? And then what this property just says, for every radius you give me, so it's 2r independent, so for every r, there's a constant number of vertices. Yeah? There's a set S, yeah? This one. And you only have S of r many vertices, so it's a constant. Yeah? And then for every number m, which is the size of your independent set you want to find, there is a natural number that depends only on the radius and m. So that if this set you've given me, this guy here, A as it's called, if this is big enough and it contains at least n of rm vertices, then it's guaranteed to have a 2r independent set of size m, which is a subgraph of it in G minus S. Okay, let's do it again, because it's probably something you can read twice without doing too much harm. Yeah? Okay, this is a graph G, and I want to find m vertices, these guys, and their pairwise distance is more than 2 times r. Yeah? This is what I want to find. But it doesn't exist, like I said, in nowhere dense graphs, because you can have a vertex which is neighbor to everyone else, and so it doesn't exist. And suppose we have such a vertex that's neighboring everyone, yeah, so we need to delete it, and maybe then once I delete it, I find this in the rest of the graph. Yeah? And this is what uniformly quasi-wideness just says. Yeah? It just says I can find a small number of vertices, and it only depends on the radius and not on not at all where I want to find it. And once I delete these guys in here, then you can give me, it's a game between us. Yeah? You say, oh, eventually, well, this is a radius I want to find. then I, as a good guy, I delete these vertices. Yeah? And then you tell me how many elements of your independent set you want to find. Yeah? This is this M. And I can tell you a number. Yeah? And once you know this number from me, you can tell me a subset A, which is big enough. It's bigger than the number I've given you. And then I find the set of vertices depending on it, which is not very big, and you have an independent set in this subset A. And so typically, if you think back of this model checking algorithm, we go through every vertex, and if its neighborhood satisfies the formula, we color it red. And then we need a 2R independent set of some size in its red vertices. And so this property would just say if you have sufficiently many red vertices, then there will be an independent set. Yeah? Actually, no, saying this might be good for model checking. I never thought about this. Yeah? That's what the property is saying. Yeah? And there's a theorem by Jarek Neschetreller and Osona Mendes, who invented nova-dense, that if you have a class of graphs closed undertaking subgraphs, then it's uniformly quasi-wide if and only if it's nova-dense. And so there's another characterization of nova-dense. So it's somewhat close to the splitter game, and you can prove one from the other if you want. Yeah? But the bounds are huge, yeah, because if you follow this proof, then this is Ramsey after Ramsey after Ramsey after Ramsey after Ramsey after Ramsey and so on. Yeah, the bound is enormous. Yeah? I mean, it's a good number of iterations of Ramsey, and this is not very efficient. Yeah? But it turns out, I mean, if you think of this for like 10 minutes, this gives you immediately a way of solving an FBT algorithm for dominating sets. Yeah? Because if you find a huge independent set, then of course you need many vertices to dominate it. So you know one of your elements in S has to be in the dominating set, and you recurse. Yeah? So it's a very nice property, this uniformly quasi-wideness, which I haven't mentioned so far. And the beauty is now, because these bounds are constant depending on R and on M only, but they're really, really huge, like I said. Yeah? And it would be very nice to make them small, because this is a good property if you want to do algorithms, but you need small bounds for it. And it turns out, if you use stability, then suddenly you can get very efficient bounds. Yeah? So what you can show, if you have an nova-dense class of graphs, then you can prove for every radius there is such a polynomial. It depends on the radius, of course, and a constant S of R. So that for every number M you give me, if I have a graph from my class and I have a set of vertices which is polynomial in M. So you only need P of M vertices, so a polynomial in M. Yeah, then I can find a subset of size at most constant S of R, and in the rest there will be an R independent set of size at least M. Yeah? So basic.
What does it use stability?
In the proof. Yeah? And so you prove it by in the synonyms. Yeah? But let me maybe read the result and then we can prove it later. So furthermore, if you actually have a bound on so for your radius R, you have a bound sort of on the excluded clique in your nova-dense class, then the number of vertices you need to delete is at most C times R. Yeah? And so even this is extremely, because you know if you're nova-dense for every radius, there's some complete graph which you can't get as a depth R minor. And this gives you some limit this gives you a lower bound on number of vertices you need to delete. Yeah? If you have a large clique, then you need to delete many vertices. This is what you get. Yeah? And all of it can be computed very efficiently, and you can use this result and plug it into all these algorithms using uniformly quasi-wideness, and the parameter dependence grows enormously. It goes from sort of manifold exponential into a polynomial. The consequence of it is if you have a class of graphs which is uniformly quasi-wide, yeah, then it's uniformly quasi-wide if and only if it's actually uniformly quasi-wide with these polynomial margins, because it's the same on nova-dense. Yeah, how do you prove this? I mean, and like you said, the key tool is indiscernibility. Yeah, because let's say I want to find a 2R independent set in a graph. Yeah? So, which means you want a large sequence of vertices, and pairwise they have distance to R. Yeah? But two elements having distance more than R is a first order property. You need two variables, and you just say the distance is R. R is a constant, so you just say, okay, there's no path of length R between them. Yeah? And so you want this, but you want a set of vertices which is pairwise of huge distance. Yeah? And this is how you get them. Yeah? You take a set A, which is long enough. Yeah? You just put it in any order, and you just take delta. Let's just go back to this definition. because I can prove this theorem to you in, roughly a few minutes. This was the definition of indiscernibility. And now we want to find a set of vertices which are pairwise of distance 2, R, let's say. So I take my set A of vertices in which I want to find it, if it's big enough. And this will form the sequence A1 to AL. And now you take this, this set delta here, just the single formula saying the distance between x and y is more than R. And this theorem here, it would just say, well, if the length of the sequence of vertices you're giving me is this polynomial in M, I will find a subsequence which is indiscernible. Well, what does it mean to be indiscernible for the formula saying the distance is at least R? It means any pair of vertices in this sequence here will have distance more than R.
Or every one has smaller.
I was waiting for this command. Yes. Or it's wrong. Right? Because indiscernibility, of course, doesn't say that all pairs of elements satisfy the formula. It just say if one of pair does it, then the other one will as well. So if you're happy, if you're lucky, not happy, if you're lucky, you will get a subsequence on M vertices so that any pair of them will satisfy your formula saying the distance is big. This is what you want. But you could also get such a sequence, and any pair of vertices would be close. But in a Nova dense class, this can't happen. Well, it doesn't work because, Nova dense just says, it's not very dense locally. If you want really large cliques, it can't be sort of all sitting together. Yeah? But this is just saying I have a fairly big number of vertices which are all close together, yeah, and pairwise and so on. And this is not really what's happening, in a sense. Yeah? There's more to the argument, but I want to give you two minutes proof. Yeah? But I think it shows very nicely how useful this property is, yeah? Because you can just, anything you want pairwise, you can just code it in first order logic, apply this theorem, get a polynomial bound, and you get something which behaves nicely in these formulas. Yeah? And of course, you need to take care what happens if none of them has a property that you want, but then you have to prove this can't happen. Yeah? And this is very powerful, and it's quite nice. And it's also not very hard. Okay, I shouldn't say this because we published it. But this paper by Maliaris and Schiller, you can actually read this. It doesn't go for every Schiller paper that exists, but this one is actually readable. It's not very long, and yeah. Selfishly, I would of course recommend if you found this interesting before reading the Maliaris paper, read this paper because this Maliaris paper is very nice. It's also very well written, and I recommend reading it. It's a lot of fun, but it refers at one point to Schiller's book, yeah, and then you have to find something on delta ranks in the book, and this is also fun, different fun. Yeah? And so this part, personally, because we wrote it, I think I would read it here, but I'm not judging, of course, no? Especially not on TV. Yeah? So it's okay. Anyway, so we get the consequence now that we have, if you're uniformly quasi-wide, then you have polynomial bounds, yeah? And which means you can actually speed up all these results. Like you can now find an algorithm running in time, which is just polynomial in k, so 2 to the p of k. Which computes you a connected dominating set of size k. Yeah? And the algorithms before using these Nova dense stuff, they had very different parameter dependence. Yeah? It's way more than a polynomial. Yeah? All right, and you get also something else. Sorry, it was taking this from a different slide. Yeah, so there's no Sebastian today, so don't worry, but there's this result here, so you can just listen to them. Never mind, you can do lots of things, and now you actually get good bound. That's the take-home message. And there's some other random results we proved because we wanted to understand these classes. And what I want to say more or less is it's worth doing it because these classes are nice and you have lots of open problems. So if you're interested in this kind of work, then this is where I would start because there's a lot to explore and there will also be lots of simple results still unproved. And it might be nice, yeah? So there might be something more to stability than just some random results. Yeah? And I guess this is what's currently going on. It's one studying interpretation closure of a sparse class, and the other one is sort of stable classes. Yeah? And so that's the end of my tutorial. So thank you very much, and thanks for staying.